Hi everyone, today a video in the Transition Metals and Inorganic Reactions series looking at catalysis. So remember that catalysts affect the rate of a reaction without being chemically changed themselves. They speed up the rate, they make the rate faster, and they're not chemically changed themselves. So whatever catalyst it is that we put in at the start, we always end up regenerating at the end. And they speed up the rate of a chemical reaction by allowing the reaction to proceed through an alternative pathway. And this alternative pathway has a lower activation energy. And if you go back to my videos on the kinetics series and cover the one that goes through the Arrhenius equation, you'll see that there's a link between the rate of reaction and the activation energy. The smaller the activation energy, the faster the rate of reaction. Remember that the activation energy is the kind of minimum energy we need to start breaking bonds, the minimum energy for a successful reaction to occur. Now, catalysts are very important in industry. They allow lower operating temperatures and pressures. That saves an awful lot of money for companies. They're also important in everyday life, such as a catalytic converter on a car, which converts harmful gases into less harmful gases. And many of them are based on transition metals. And the key thing, again, as we're seeing throughout this series, is that the really key thing that defines the properties of the transition metals tends to be that they have these partly filled d orbitals. And these part-filled d orbitals can form weak bonds with reactants. Now, when they do this, it has a dual effect. The first is by forming a bond, a sort of temporary bond, if you like, a weak bond to the reactants. It actually weakens the bonds within the reactants themselves. That lowers the activation energy. It takes less energy to start breaking that bond. It also means essentially that they kind of provide quite often a surface for a catalyst, and so they can hold a surface for the reaction to take place on. And so they can often hold the reactant molecules close together, but also in the correct orientation for a reaction. And so we often talk about our collision theory, and for kinetics, this idea that not only do we have to have this minimum energy to start reacting, this activation energy, the minimum energy to start breaking bonds, but we also have to have our reactants colliding and hitting each other in the correct orientation for a reaction. And so the first type to talk about is a heterogeneous catalyst. Now, what heterogeneous means is that our catalyst is in a different phase to the reactants. Now, we can think about phases as being the kind of state symbols that we put on our chemical reactions, so solid, liquid, gas. But also phase can be a little bit more complicated than that. It can actually, there can be several types of different phases within a certain kind of physical state. So quite often it's very common to have potentially two different liquid phases within a certain reaction. And so an example to think of this would be oil and water. Those are two technically different phases, even though they are both liquid. You know that oil and water hopefully doesn't mix, and therefore one sits on top of the other. And therefore, these are actually different phases. We say that there is a phase boundary between the oil and the water, that they don't mix together. When you do organic reactions, very typically you end up with an aqueous layer and an organic layer. The organic layer is what contains your product. The aqueous layer is typically what contains the water or any kind of salts that you've used. And so typically phase can be thought of as solid, liquid, gas, or it can be slightly more complicated in terms of different liquid phases that don't mix. But for heterogeneous catalysts, what we usually mean is that the catalyst is a solid while the reactants are liquids or gases. And so we have different phases there. And so their catalytic action happens on a solid surface. And because they're in a different phase, one of the big advantages of a heterogeneous catalyst is that separation of the catalyst from the product is very, very easy. If we think about just doing an actual reaction with a heterogeneous catalyst, because it's a solid and our reaction typically might take place in solution, it's very, very easy to get rid of that catalyst at the end just by doing some sort of simple filtration. And so typically, if we think about the steps that are involved in a heterogeneous catalysis, the first is that our reactant will bind quite weakly to the catalyst surface. And so on the kind of diagram shown here on the right, the cartoon of how this works, you can see that is step number one. And so you can see that our reactant molecule is kind of bonded quite weakly to the catalyst surface using those partly filled d orbitals. And this step is actually called adsorption. Note that it's not absorption with a B, but adsorption with a D. Adsorption means a temporary sort of binding to that then can be released later. If it was absorbed with a B, that would mean it would be permanently bonded to it. Here we only have this weak temporary bond, and so it's called adsorption with a D. And this weakens the bonds, as we said, within the reactants. Now, essentially, as shown in this cartoon on the right, step number 2 is we have another reactant molecule approaching the catalyst. But the idea is that over these kind of steps of 2 and 3, we have this chemical reaction taking place because the reactant molecules are held close together in the specific orientation that's going to allow them to react with the lower activation energy. And so our chemical reaction takes place on this surface. And then finally, either step 3, as I've said on the left, or step 4 in the cartoon on the right. Essentially what happens now is we've done our chemical reaction, we've formed our products. The key thing, of course, is that our products are still essentially weakly bound to our catalyst surface. We need to release them, and this is why it's important to have these weakly bound sort of molecules. The reason why it's not a strong bond is because we have to release our products at the end. And so the products are released from the surface. This is called desorption. And the catalyst ends up being regenerated. We've not changed the surface of that catalyst. Other molecules can then come in and repeat the same reaction. And so, as I said, an example of this was a catalytic converter, and this is exactly how a catalytic converter works. Typically, it's a kind of platinum-rhodium type catalyst, often a honeycomb type catalyst. And basically, it takes these kind of harmful gases, carbon monoxide, nitrogen monoxide. These are absorbed, adsorbed with a D, and the bonds get weakened within them. The reaction takes place, and they end up forming CO2 and nitrogen N2, much less harmful molecules. These are then desorbed from that catalyst surface. Now, catalysts are often expensive, and so they should be highly efficient. This comes back to the idea that a catalyst is typically regenerated at the end of a reaction. However, they're not regenerated every single time. Eventually, your catalyst will essentially not work any longer. Now, since the catalytic activity takes place on a solid surface, there are a couple of ways that we can make a catalyst last a bit longer and act much more efficiently. The first is to increase the surface area, and this goes back to our sort of very simple collision theory and kinetics, this idea that if we have a greater surface area, think about having one chunk of metal divided now up into 4 chunks of metal, as I've shown here on the kind of middle left. These 4 smaller pieces have additional surface area, additional space for molecules to be able to collide with it, for molecules to be able to essentially adsorb onto the catalyst surface. If there's more space for that absorption to occur, faster rate of reaction, that catalyst is more efficient. So we can increase the surface area. The second one is to actually absorb it onto an inert support medium. And this has a kind of similar idea that it increases what we call the surface to mass ratio. And so again, that increases this kind of efficiency of a catalyst. Now, catalysts, as I said, don't last forever. Over time, the surfaces can become covered with unwanted impurities. So it's not just our actual reactant molecules that can bind to our metal, but it's other things that we potentially have in our reaction mixture. If you think about our catalytic converter, there's lots of other things that potentially are around in the air and the environment that could also bind to this catalyst. And typically, sometimes these impurities are actually, they bind to our surface so strongly that they don't desorb off. And so they then leave less sites available for our reactant molecules to come onto. And so this process is called poisoning. This is the poisoning of the catalyst. And so these molecules, these impurities that poison it, can compete for binding with the catalyst, and they reduce the space available for the actual reactants to bind. And so the example here, kind of in sort of middle to right of the middle of the screen here, is that we have these hydrogen molecules are actually what we want to be adsorbing onto this sort of platinum ruthenium catalyst. However, you can see that as more more carbon monoxide, more CO molecules actually end up binding onto this, this CO molecule inhibits the reaction. It takes up the space that the hydrogen would take itself, and so therefore it makes our catalyst less efficient. And eventually our catalyst doesn't work at all, and therefore we have to throw it out. And therefore that can often be the main cost of catalysts, having to replace them. Sometimes as well, this finely divided catalyst can also be gradually lost from the support medium over time, and again it would require therefore to be replaced after a certain amount of time. And so the final fact to think about is this strength of adsorption and desorption is really important. Now, some metals will form bonds that are actually too strong to release the products. So rather than forming weak bonds to the reactants using those d orbitals, they actually form quite strong bonds. What this means is that while it holds the molecules very strongly in the position they need to be able to react, once they've reacted to form the products, they can't be let go, they can't desorb. And so an example of this would be tungsten, for example. On the other hand, you have some metals that tend to form bonds that are too weak to the reactants. An example of this would be silver. And so what this means is that essentially we can't even hold our molecules in the correct orientation or hold them close together for reactions to occur in the reactants. And therefore, essentially, they are far less efficient as well. And so we have this idea of a kind of Goldilocks effect. It's not too strong, it's not too weak, it's just right to be able to hold these molecules in exactly the right orientation and close together to react, but they're not strong enough that it's able to release them at the end as products. And typically we found that kind of platinum and nickel have this Goldilocks effect. They can absorb and desorb the best, and they've found the most used in catalysis. So some examples of heterogeneous catalysis. The first, one of the most widely known examples is the Haber process. So the Haber process is how we make ammonia. Ammonia is incredibly important really for fertilizers and therefore kind of food production and crop growth. Now the catalyst for this is finely divided iron, or pea-sized lumps of iron. Now the reason why it's finely divided is because that increases the surface area, therefore makes our catalyst more efficient, as we said on the previous slide. And so we have our reaction here of nitrogen and hydrogen gases reacting together to form ammonia, NH3. Now this iron catalyst tends to last about 5 years before it gets just completely poisoned by impurities in the gas stream. There's things like sulfur compounds that tend to bind to it too strongly. They can't get released, and therefore we have to, after about 5 years, replace this catalyst. The second is the contact process. So the contact process is actually the process in industry that produces sulfuric acid. And so sulfuric acid is made from sulfur, oxygen and water. And the really key step in it is to take sulfur dioxide, SO2, react it with oxygen and make sulfur trioxide, SO3. And it's catalysed by this vanadium oxide species. So vanadium 5 in the +5 oxidation state, vanadium 5 oxide, V2O5. And this happens in 2 steps. So the first step is we take our SO2, our sulfur dioxide, react it with this vanadium oxide. This creates SO3 and another form of vanadium oxide, now V2O4. Think about our sulfur dioxide being oxidized, our V2O5 being reduced in terms of our oxygen. And then the second step is to take this V2O4 and react it with the oxygen, and this creates V2O5. And so if we combine these 2 equations together, essentially what we'll see is that our V2O4 cancels out, the V2O5 also cancels out, and so essentially you can see that our V2O5, our vanadium oxide in the +5 oxidation state, has been regenerated there at the end. It's unchanged. And so our overall reaction, when you add it together, becomes 2SO2 plus O2 to 2SO3. And the key thing is that these 2 steps, each of these 2 steps, has a lower activation energy than the uncatalyzed single step. So simply taking sulfur dioxide, reacting it with oxygen to form sulfur trioxide, has a much higher activation energy than these 2 steps involving the vanadium oxide. And again, it's this idea that our vanadium oxide allows it to lower the activation energy, because by forming weak bonds to the reactants, we lower that activation energy by weakening the bonds within the reactants, but also holding them together in a very close proximity and actually in the correct orientation to be able to react. Now, the other type of examples that we need to know is something called a homogeneous catalyst. And so, as you can imagine, from a heterogeneous catalyst, it's the opposite. Homo and hetero are opposite. And so a homogeneous catalyst is where we have our catalyst being in the same phase as the reactant. So this might typically be that we have a solution phase reaction, something happening in solution, and our catalyst is also present as a solution, essentially, present in that solution phase. So everything's in the same phase as each other. Now, typically when we do homogeneous catalysis, we form intermediate species. And so a couple of examples here to talk about. Here we have the peroxidized sulfate ions and iodine. Now, the peroxidized sulfate ions, they have quite a complicated name. Essentially, they're just S2O8 2- anions. Now, these actually oxidize iodide ions to iodine, and the reaction is catalyzed by Fe2+ ions. And so the two steps are as follow. We take these peroxo disulfate ions, react them with Fe2+. This ends up producing our sulfate anion, SO4 2-, and two lots of Fe3+. So we've gone from Fe2 to Fe3+, and our S2O8 2- has gone down to SO4 2-. The second step is then this Fe3+. Our Fe3+ here is an intermediate species. We formed it in the previous step. We're now using it in this step. So overall, when we add our two steps together to make the overall reaction, this will cancel out. And so the Fe3+ ions react with our iodide ions and end up producing Fe2+. We regenerate that catalyst, the Fe2+, and we make iodine. And so the overall reaction, if you add together these first and second steps, is that your peroxo disulfate ions react with iodine, and they produce they react with iodine, and they end up producing the sulfate anions, and so they react with the iodide ions, produce sulfate anions and iodine. Now, the key thing again with this is that these two steps have a lower activation energy than the uncatalyzed just one-step route. And you can actually kind of see this purely from the charges that are present in our reaction. The uncatalyzed reaction is very slow. The overall one-step reaction is very slow because it takes place between two negatively charged ions. You have your peroxo disulfate ions, 2-, and your iodide ions, 1-. The same charge, negatively charged, they repel. So that has a much higher activation energy. You can think that we have to put a lot of energy in to force those two ions together and react because they want to naturally repel. So it has a very high activation energy. You can see that the two steps that we catalyse with the Fe2+ always take place between a positively charged ion atom and a negatively charged anion. So the first step is the peroxo disulfate ions, negative, the ion 2+, positive. The second step is the ion 3+, positive, reacting with the iodide ions, negative. So because we have this positive-negative electrostatic attraction, because they are attracted, we have this attraction. The combined activation energy is lower than this uncatalyzed reaction. Now, an interesting thing is that actually Fe3+ ions can also catalyze the reaction. And so in this case, if we start with Fe3+ ions, we actually have the second step happening first. It produces Fe2+. Our Fe2+ is the intermediate. The first step then happens, and we end up reproducing Fe3+. So just be careful as to, in an exam, potentially they might say to start with Fe3+ or Fe2+. Just be careful as to which one they say to start with. And over on the right, you can see we have this enthalpy diagram, so energy or enthalpy up the y-axis, extent of reaction along the x-axis. That red dotted line is our uncatalyzed reaction. And so you can always see we always start, we have an exothermic reaction here, products lower than the reactants. And we draw our curve that starts from the reactants, goes up to our transition state. Remember, the transition state is our kind of intermediate. It's the kind of where we've half made bonds, half broken bonds. It's kind of that middle point between the two. It doesn't actually exist as a chemical species. The transition state is the energy maximum. The chemical species that exists there is called an activated complex, and typically we can never isolate these. They're just too unstable. And then you can see that underneath it you have this two-step catalyzed reaction. And you can see that each of these transition states, remember the transition state, our activation energy is always measured from the reactants to the transition state. You can see that our activation energy here actually is much lower than it was when it was uncatalyzed. Because we have this reaction between oppositely charged ions as opposed to a reaction between the same ions. And when we do that, we actually form an intermediate. So we have transition states for every step. But in this case, we actually form an intermediate. This intermediate exists. It's not just something that's too unstable. It actually does exist. And therefore, we can take our second reaction starting from that point. So the final type here to look at of the homogeneous catalysis is an example of something that we call autocatalysis. Now, autocatalysis is when one of the products of a reaction is a catalyst for that reaction. So this isn't a case of we have our reaction and we're going to put a separate catalyst in to speed it up. Actually here we don't put a catalyst in, but the reaction rate increases initially over time because one of the products of the reaction can actually act as a catalyst. And the example we need to know for this is the oxidation of ethane dioic acid. That's a dicarboxylic acid with a 2-carbon backbone. by acidified manganate 7 ions. Now, this autocatalysis type of reaction always has this kind of same shape of concentration time graph, the same kind of kinetics. The reaction will start pretty slowly at the uncatalyzed rate, because we don't put any catalyst in at the start. It is our product that is the catalyst. So at the start, when we have no product, and at the very start of a reaction when we're just having very, very small concentrations of product forming, it starts slowly at this uncatalyzed rate. However, as the reaction proceeds, we make more and more of our product. Our product is the catalyst, and so that concentration of the product catalyst increases. The reaction therefore speeds up, and it speeds up to the catalyzed rate, the much quicker rate. But then after that, we get our standard kind of kinetics of we have a reaction that is going at a certain rate, and over time that rate decreases because our reactants get used up. You can think of our effective concentration of reactants falling, them being further away from each other in collision theory, and so we have far less successful collisions, and therefore the reaction rate goes down. And so we can see this on our concentration time graph over on the right, that we start off with basically a near horizontal section. This is our reaction starting very, very slowly. Right at the start of our reaction, high concentration of the reactant, hence a low concentration of the product. Over time, you can see that the gradient of that line, the reaction rate, increases until the point where we get this almost kind of vertical portion of the graph. This is where our reaction is speeding up, and eventually it reaches the fully catalyzed rate. And then, as we said, like most reactions, we then end up with our reaction rate slowing again before it eventually comes to a halt, because we're now using up the sort of last remaining reactants that are there. And so our concentration of reactant falls all the way to 0, and our reaction rate stops. Now, the actual catalyst for this oxidation is manganese ions, Mn2+ ions. And so these aren't present at the beginning of the reaction because they are a product of our reaction. But once some of these Mn2+ ions have formed, it can react with these manganate 7 ions, MnO4-, to produce Mn3, the manganese 3+ ion, as an intermediate species. This Mn3+ then reacts with our ethane dioic acid, and it's written here as the oxalate anion, C2O42-. That's just the ethane dioic acid that's been deprotonated, essentially. And so our overall reaction, you can see there at the bottom, the key thing is that we have our oxalate anions here, our ethane dioic acid, essentially. We have our manganate 7 ions as reactants, and you can see that one of the products of this is our Mn2+ manganese ions. And you can see we've oxidized this ethane dioic acid to this carbon dioxide, a higher oxidation level product. And so initially we don't have any Mn2+, as we said, but as the reaction goes on, it starts slowly. We make a little bit of the Mn2+, that product, and then this can act as our catalyst. And so here we have our 2 steps. The first is these Mn2+ ions that we've made, reacting with these manganate ions, the MnO4-, our reactant. And it's acidified, we have 8 in there, and this ends up producing 5 lots of the Mn3+ manganese ion, 3+ manganese ion, plus water. Now remember that Mn3+, the manganese ion, is our intermediate species. This then reacts with the oxalate anion here, the ethane dioic acid, and it produces CO2, and it reforms the Mn2+. Remember, the Mn2+ is our catalyst, so it gets reformed at the end, chemically unchanged. Now, to make the overall reaction for this, like you've seen with redox reactions, you can combine redox half equations together by cancelling out the electrons, cancelling out the intermediate species. The same thing happens here. We haven't got electrons, but we do have our Mn3+ ions that we know are the intermediate species. And so we want these to cancel out. We have 5 on the top as a product, 2 on the bottom as a reactant, and so we have to times the top equation by 2, the bottom equation by 5. That gives you 10 lots of Mn3+ on both sides. They cancel out, and then your overall equation ends up being 2 lots of the manganate ions plus 16H+, plus 5 lots of the oxalate anions, going to 2 of the manganese 2+ ions, 8 waters, and 10 lots of CO2. And this reaction can be really easily followed using a colorimeter. So remember, the colorimeter essentially looks at the absorbance. Essentially, it looks at how concentrated the coloured ions are. And what we can do here is we can actually monitor the concentration of the manganate MnO4- ions because they're very deeply purple, very strong purple colour. And so because they're very strongly purple, we can use this colorimeter to essentially measure the absorbance and therefore monitor the concentration. Because as our reaction proceeds, we turn our manganate MnO4- ions into our manganese Mn2+ ions. Now the Mn2+ ions are very pale pinks, they're almost colourless, and so you get this very, very clear colour change of the very deep purple to kind of essentially colourless, very pale pink. And so this colorimeter allows us to monitor the concentration because the colour essentially seems to fade. So time to have a go at some questions here. There's not too many questions because the real part of this video is to kind of just go away and learn the equations from these types of different types of catalysis. There's a few questions here, so have a go if you like. Pause the video and the answers will be on the next slide. So the first question here was to essentially there was a list of different types of catalytic reactions and to say whether either they were homogeneous or heterogeneous. So remember, our heterogeneous catalysis is where our catalyst is in a different phase to our reactants, often a solid, where our reactants are liquids or gases. Or homogeneous was where our catalyst was in the same phase as our reactant, and that's typically in the liquid phase. So the first example is our platinum and rhodium gauze catalyzing the breakdown of NH3 into NO. Well, here we're given this platinum and rhodium gauze. That's literally a solid to solid support medium, and therefore it's a heterogeneous catalyst. Typically, if you're just literally given a metal rather than a metal compound, if it's typically just a metal, that is always typically a heterogeneous catalysis because it's a solid metal. The second is nickel catalyzing the hydrogenation of ethene. Again, this is a heterogeneous reaction. Remember, the hydrogenation of ethene is essentially converting the ethene into ethane, making the unsaturated molecule a saturated molecule. And the way that it does this essentially is it holds the reactant molecule in a specific orientation and holds the alkene and the hydrogen close together such that they can react by reducing the activation energy. C was enzymes in yeast converting sugar into ethanol. This is a homogeneous reaction. So this stuff all tends to take place in the aqueous phase. And then finally, these platinum, rhodium and palladium catalyzing the reaction in a catalytic converter. A catalytic converter is a heterogeneous reaction. Again, we have this kind of these metals acting as a solid support system, often a honeycomb kind of system. And I've drawn here the reaction, as I said, it takes these more harmful gases, CO and NO. CO indeed is definitely quite a poisonous gas, toxic gas, and it converts it into CO2 and N2. And the second question was to make a list of the advantages and disadvantages of the different type of catalysis. Now, I didn't really talk so much about this, but hopefully you've had a go and had a think at why one type of it might be better than the other. For heterogeneous catalysis, we said that one of the big reasons that it was useful was because that typically there was no need to separate our catalyst from the reagents. It wasn't very difficult to separate them together. Typically, our heterogeneous catalyst is a solid, everything else is a liquid, and so it's very easy just to filter off that catalyst and you end up with a pure product. And heterogeneous catalysis actually ends up being more widely applied in industry because they tend to be slightly lower costs. So it tends to have a greater economic impact certainly in terms of how you actually, when you finish your reaction, how you work up that reaction, how you get your catalyst out, able to be reused, and how you get your pure product. It's far cheaper for heterogeneous catalysis. And typically the materials tend to be a bit lower cost as well. However, there's something called limiting mass transfer to and from the active site of our catalyst. So when we say active site, we actually kind of mean very similar to how we have an active site in an enzyme. Remember, an enzyme is just a catalyst itself. It's a biological catalyst essentially. So we have an active site where the actual reaction will take place. Because it's a solid typically though, and our reactants are often liquids, we actually have to get our liquids to actually physically move to the solid reactant. And so this kind of rate of it moving, this what we call the mass transfer, literally moving the mass, tends to be quite slow. And actually, heterogeneous catalysts can be quite difficult to challenge, because quite difficult to study, challenging to study, is because actually this active site where the reaction actually takes place tends to be a bit ambiguous. We're just dealing with solid metals typically, and these kind of big sort of solid structures, they're quite difficult to study. On the other hand, for homogeneous catalysis, essentially we have almost the opposite of all of these points. So we talked about the fact that it was quite a slow rate for heterogeneous because you had to get liquids and solids to mix. For homogeneous catalysis, everything is typically in a liquid phase, or at least everything is in the same phase. And being in the same phase means that we have typically faster rates of reaction and faster rates of diffusion, literally the moving of the reagents and products to and from the active site, because they're all in the same phase. It's also much easier to study homogeneous catalysts, and therefore this active site, this part of the molecule where the actual reaction occurs, can often be studied more easily, and therefore we can design other catalysts quite easily as well and control the actual reactivity and selectivity. However, because homogeneous catalysts are in the same phase as our reactions and products, the separation of the catalysts from the products is often much more difficult. And it's actually much more difficult to obtain a pure product. Quite often you're still left with trace amounts of your catalyst in there, which for some applications, for example, if it's being used in medicine or biological applications, could be even fatal if there's a tiny amount of catalyst left in there. And so this is particularly important for pharmaceuticals and agrochemicals, things that we're going to kind of either inject into us or take through the mouth or eat or something. If we've even got very, very trace amounts of toxic metals, that can be potentially even fatal. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on our tuition website. I offer online tuition for chemistry, so please check out the tuition pages if you're interested in that. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.